This is a technical version of our adaptive learning pipeline framework. So here's an outlined and detailed process to achieve GEC's system goals, starting from a student's first activity on the platform, running through our robust data science pipeline, C-Core, and culminating in the delivery of adaptive content-based on-time series causal analysis and adaptive control mechanisms. This integrates our goal of managing causal influence vectors across metrics with the causal lag for Granger causality and transfer entropy analysis set at 5. So the causal log set, or the causal lag set at 5. So we're analyzing across a multi-dimensional field of complex causal dynamics. For example, social interactions with teachers, with parent interventions, with peers. Number 2, with attitudes and motivations about school, about friends, about other things. Psychometrics, which includes the big 5, but more. Study habits, covering regularity or duration of study sessions, completion rates, problems and lessons. And language skills, reading, listening, writing, speaking, and more, like grammar and vocabulary. Academic skills like math, science, social studies, and language arts. So again, this is a multidimensional field of complex dynamics. The full cycle processing pipeline framework. We start with number 1, student interaction and data generation. And the description of this, that there are trigger points, which are student logs into the platform and starts interacting with the content. And then these interactions generate event data as the student engages with various LMS modules, so like navigation activities, study habits, responses to challenges, and more. And then what are the data sources? Well, there's the behavioral activity logs, for example, time spent, pages visited, actions performed, content consumption data, videos watched, articles read, exercises that have been selected. Then there's student reported data, or even other human reported data from the school or the teacher or the parent. So anyway, reported data like surveys, social connections, attitudes, motivations, reports on those types of things. And then there are external interventions, which I mentioned. Then number 2, after the interaction and data collection here, number 1, then we go to data acquisition, governance, and preprocessing. So the goals here are to ingest, validate, and preprocess the incoming data from storage, and so that we can ensure the compliance with governance and quality requirements. So we want to also establish the temporal alignment for Granger causality and transfer entropy, because we're going to be taking time series data. So we may have, for example, each student might have 50 data points, and a timestamp 1 is a snapshot of all 50 states of that data. Time series 2 is a snapshot of the same 50 data points, but at a different point in time, a consecutive sequence point in time. And we need that data flow. We need to look at the change delta between these different data snapshots. So anyway, we got the steps here. Number 1 is data ingestion, where we're using Spark streaming, and then Kafka for live streaming. We may use Airflow in certain cases, but basically we're going to stream event logs. We're going to look at the interaction data and metadata, for example timestamps and features and things like that. Next we have storage, which is structured data through tools like Postgres and BigQuery and Redshift. Then vectorized data, which is Postgres SQL with pgvector or weave8 for embeddings. Step 2 is the pre-processing, where we may use great expectations for data cleaning, with format checks, data types, missing values and outliers. Then temporal alignment for causal analysis, so time series generation, and then there we resample at the set time intervals where necessary, either daily, weekly, hourly, minutely, by the minute, or even under shorter circumstances. Like with good processing using virtual machines, and we can actually achieve like a half a second, like 400 millisecond cycles. I don't think we need that in this particular learning process, but we can achieve that. Then we're obviously, we want to do the feature engineering, which is cross-feature generation. So looking, for example, at attitudes versus the study habits. So how do attitudes affect study habits? And then initial dimensionality reduction, where we're going to use UMAP and principal component analysis and tools such as this to get reduction, our truncated data. Then when it comes to government and orchestration, we want to again use Airflow, or Prefect is fine too, in some cases, for unified processing and other orchestration pipelines. Okay, the third tool in the pipeline, the third module, is the advanced feature extraction and dimensionality reduction module. And the goal here is to create useful reduced representations of data variables for downstream modeling, given the high dimensionality of the student metrics that we're dealing with here. So step one would be feature extraction, and we're looking for the latent features, and we're using like scikit-learn and Spark ML libraries. We're looking at the tabular data processing, and then we get the deep embeddings from TensorFlow and Hugging Face. So that's for sentiment analysis, nearest neighbor tagging, and things like that. And then for dimensionality reduction, UMAP for visualization or as input to the time series models, and then we'll experiment with TDA-based models for, like for example, persistent diagrams for complex relationships if we need it, and I think we will. And then the output would be that the features have been sorted as high-dimensional embeddings for causal analysis. So now we're ready. We're getting closer to being able to do causal analysis, but the first step in that would be number 4, the statistical analysis model and time series inference. And so our goal here is to establish the temporal causal links using Granger causality and transfer entropy. So basically we set the causal lag to 5. We can do more or less, but we're capturing the medium term dependencies between variables at lag 5. And then the steps would be, first of all, time series formatting. So we reformat the data outputs into the proper time series data sets. So we split these macro metrics, for example, study habits, into their micro units like regularity or duration or completion rates. And then what we'll do with Granger causality is we're basically analyzing the primary temporal causality. We can get secondary and tertiary causality with Granger too. Like does one factor Granger cause another factor, basically. So we're testing how each student metric, for example, peer social interaction, how it affects our study habits, and then it predicts others after the lag adjustment. And then we can use stats models for regression over these 5 lag time windows. And then where transfer entropy comes in, we're looking for non-linear causation, and so we're modeling that. We're modeling these dependencies between variables where Granger fails. So peer interaction versus psychometric big 5 traits, and it's not just looking for the primary causal relationships. It's also measuring the magnitude or the energy in that relationship. And then for the output, we're looking to generate the raw causal graphs. So this would be the DAG graphs, or the directional acyclical graphs, where we have the weighted edges that represent the strength of these causal relationships, and it's all mapped. Okay, and then we want to go to structural causal inference. This is the secondary analysis where we would be using DoY, the Python library, to validate these causal structures obtained from Granger causality transfer entropy. So we use Granger and transfer entropy to detect the causal relationships, and then we use DoY to basically validate that. And we want to eliminate the spurious correlations or the confounders from the Granger and transfer entropy analysis. So step 1 is we input the time series causal graphs. So we convert those Granger transfer entropy graphs into these DAGs, And then number 2, causal inference tools. We use do-why to compute the potential outcomes. So we apply these backdoor adjustments, or we block the backdoors, we look for we control for confounders, and then, for example, does the parent interaction as it relates to the academic skills, is that detected causal relationship, is that a spurious link driven by motivation? So, for example, we're looking for these false positives, and then we will do simulations and data analysis. And so, if necessary, we can simulate these potential outcomes with what do they call it, digital twin simulations and stuff like that, using econ-ML or other synthetic data set augmentations. And then we want to refine the causal graph. So we want to output high confidence causal vectors. So we're not just relying on transfer entropy and Granger causality. We're actually taking that and doing further confirmations. Okay, finally, once we have that confidence, that high confidence causal influence vectors, we can go to module 6 in the data science pipeline, which is machine learning for predictive modeling. And our goal here is to use the machine learning models to predict student success pathways given those causal metrics and variables that we've just confirmed. And the steps there are, first of all, to train the models. So we're going to use, for example, XBoost and LayGBM or similar models for probabilistic execution of causal rules across domains. So social as it affects attitudes, as it affects academics. So we'll be doing training on that. And then hyperparameter optimization. So you may be utilizing Optuna or grid random search to optimize each pipeline. And then for real-time serving, we're going to develop these ML pipelines for real-time prediction and intervention effectiveness. So using SageMaker, using TensorFlow serving, using Kserve, we want to be able to affect real change in the students' learning dynamics. And that leads us to pipeline module number 7, where it's the real-time feedback and adaptive control system. So we want to go ahead and generate these real-time changes to the learning paths based on our causal analysis now that we have that. And so there's a control system architecture where we need to be able to implement these feedback mechanisms. And so we want to predict the potential intervention outcomes for each individual student, and then we want to apply Python control or simple PID for closed-loop adaptations. And then as far as action generalization, we want recommended interventions that are based on these direct causal vectors. For example, we want to improve peer interaction in order to boost the students' attitudes, improve their attitudes. And then we'll be using the machine learning predictions, for example, which intervention will work best to do that. And then we have to think about LMS integration. So we have to push those adaptations back into the LMS. So we might be recommending different content, or like videos or interactive lessons. We might be changing the students' pacing, so making them linger longer, or allowing them to go faster, or to change the order, to change the scope or sequence. Notifying the parents and teachers if intervention is recommended and what those interventions might most effectively be. We might want to assign peer collaborations or study buddy sessions. We might want to populate prompts for the AI or the LLM counselor interactions. So we will have a AI-based learning coach that can counsel them on some of their strengths or weaknesses, you see. And then number 8, finally, the student activity resumes. This completes the feedback loop. Again, as they resume their activity, they're generating more data, and rinse and repeat. The whole process runs again in a feedback loop. So the goal is to go ahead and capture the effects of these implemented system recommendations on the system's performance, and thus enabling learning cycle improvements. And the steps are to go ahead and record data after the adaptive changes, and log those post-intervention interactions, and assess the direct impacts via this causal scoring. And then just repeat the full pipeline. So we feed the new data back into the pipeline, closing the loop and refining our predictions. So the final COM is a truly adaptive, causally informed learning management system that personalizes learning for each student in real time, while transparently explaining why those changes occur based on time-dependent causal analysis. And we haven't talked much about that, but that's where the explaining why, we have an explainability layer that I've not discussed here. Basically, it's integrated dashboards for observing and analyzing the decisions that have been made, so you have governance, you have human in the loop oversight and governance on the entire system. And then in the conclusion here, this I think important to understand that although these case models, this use case models the stepwise process in a single cycle of feedback system that continually models and controls for learning on a learning management system. This same pipeline, this same causal control automation can be applied to other processes across a wide range of businesses or process management platforms. So IBOS, or the Integrated Business Operations System, this LMS is only one component. We have HR management component, we have the financial component, we have, for example, sales and marketing automation. It could be even IoT edge services that have the control and the feedback systems. The LMS is only one component. There's these other potential components, and some that we've already built, some that we have that are still aspirational for us. But the goal is toward a suite of business and learning solutions over which causal control can operate to balance not only the individual modules, and here's the point, because up until now we've been talking about balancing just the learning management module. But imagine that learning management module as a one module among a suite of modules, and we want to balance the entire collective of the operations and processes to maintain optimal balance and equilibrium over the entire business ecosystem and learning ecosystem. So what I'm saying is this same presentation here, although we're applying it in a focused way just to a learning management solution, that this same pipeline could service other business modules and services and platforms.